We'll just call today miscellaneous, as that is a good miscellaneous question. So we're talking about a torque on a current carrying loop in a magnetic field. Now, it won't always have a torque, but let's establish a region of space that has a magnetic field. Something like so. Let's have that magnetic field going upwards. There we go. Yeah, I'm trying to draw something nice for a change, and my morning was funny. Some kids are coming into my class late this morning, and so I go to get my door because it's locked, or I was going to go lock my door, and the officer is trying to wrestle and calm down a student right against my door. I'm like, this is an interesting way to start the day, for sure. There's all these kids around yelling at him. So, of course, I stay out there. I don't realize that a massive fight had broken loose just on the other side of the stairwell from my room this morning, just before first period. These kids. And I keep thinking, I've got important things I need to do today, things I want to talk about with my students and all that, but I don't know how you guys can even walk around out there sometimes. So we're talking about this, right? The one we did in class, we talked about if you were trying to turn it yourself, you would encounter a torque, but you're saying that I already have a current in the loop. I'm not trying to generate a current in the loop, right? All right, so let's consider first, do we get a torque on it if it's in the, if it's like this, inside my region of space with a current in this direction? Would there be a torque on this loop? So I prefer to see if Kyle can figure that out, since he's the one who asked. So at this point on this side, the current would be passing into the screen, and it would be going around, and then on the other side it would be coming out of the screen like that. Would there be a torque on this? You have 4 sides to check. And so, right-hand rule it and see. So the only way to figure it out is there going to be a torque on this loop?
No.
Yeah?
I think so, yeah.
Well, to do so, we need to figure out where the forces are, and from there we can construct the rest of the problem. So I'm going to start, I've got A, B, C, and D to see whether there's the forces that would cause a torque. I'm using force equals IL cross B as my means for determining the direction of the force. I'm just going to use the right-hand rule. My pointer finger is in the direction of the current. My middle finger is in the direction of the magnetic field. Right? So starting where A is, I point my finger into the board. My middle finger's up, and it looks to me like the force on this wire will be this direction. You guys all with me on that? So let's go to B. B is to the right. So I point to the right, magnetic field up. That suggests the force is towards the center of the loop. So, right? C is out of the board, magnetic field up, so that's going to be to the left. And I'm thinking that the force on D is towards the center of the loop. So I don't think there'll be a torque here. Will it change if I reverse the direction of the current? I mean, it will. The forces will all change, but they're probably just all going to be out and point away from the center of the loop as opposed to towards the center of the loop. So I don't think there's going to be any torque here. So this arrangement doesn't produce a torque. You all right? Everybody understand? So what do you think? How should I position this to produce a torque?
What if you went vertical?
All right, what if I went vertical? Well, you can try that. Something like that. So now, like so. So I'm noticing first by doing this that no magnetic field passes through the loop. Are you guys noticing that? So I've kind of made it so that there's no current flux, but if I keep my current in the same direction as before, like that, I can begin the process of trying to, again, identify if there's what direction of the force is on each of the 4 sections of the wire. So I'm just going to call out 4 people. They're going to tell me what direction the force is. Ready? I'm going to pick 4. Kyle, you're on A.
Is it downwards?
I don't know. I'm asking you. So A has a current that is, based on what I'm drawing, is into the board. And C is out of the board. I think D and B are self-evident. So
Oh no, that's straight up.
I put into the board, magnetic field up. Looks to me like the force on the top of that wire is to the right. That's how the right-hand rule seems to work for me. Good. Reagan, B. Well, it sounds like you're asking me. Philip? Colin? What's that? So 3 people, all on kind of a diagonal line, chose all 3 of them, 3 answers. The force is downwards. Is there any way I can rotate my wrist to make my middle finger align with the magnetic field? Not unless I completely go straight up 180 degrees. Sine of 180 degrees is 0. So there's no force in that wire. All right, so C, out of the board. Zoe, what's the direction of the force on that wire?
Left.
Spoken with authority. I'm going to believe you. And can we dispense with D, since we know that it's probably a similar case? It goes in the same direction as the magnetic field, so there'll be no force on that wire. There is a torque now. What is the size of that torque? Well, now we need to come up with some pieces of information that we can use to define the shape and size of this. Things like we know the size of the currents, so now we need size of the box or the size of the loop. So I'm just going to make up stuff. What do you want here? We can make the loop L long and, I don't know, L wide, make it a square. Is that fine for you guys? You don't have to, but, that seems not unreasonable to me. And so the force is going to be ILB. That's the size of the force. There's a torque. Torque is going to be R times F times the sine of the angle between, and be careful, this is the angle between the force and the torque arm. Based on the way I've kind of drawn that would be this angle, which is 90 degrees. Right? It's 90 degrees from the standpoint of the relationship between the force and the torque arm. Now, R here has got to be careful. That's from the pivot point, and based on the way this is, it's going to pivot about its middle because I have two equal but opposite forces that are acting in opposite directions on top and bottom of this thing. So it'll pivot about its middle. Fair enough? So R is going to be L over 2. The force is going to be this stuff, ILB, sine of 90 degrees. And oh yeah, there's two of those. And that's why we get I L squared B, or I times the area times B. And although I don't want to prove this, you can prove that if it's a circle, you'll still get this. And you smarty pants mathletes love to tell everybody all sorts of stuff. Do it. You can do it. It's a pretty straightforward integral summation. So I'm not going to do it because I probably would fail in front of you, and I don't want to do it that way. But a lot of people like to tell me how to do things, so you should try it. It's not actually terrible. You just have to be able to integrate around a circle. You guys are smart. Try it. But if not, fine. Area, if you do the circle, don't expect to get A. You'll get pi r squared. But, it'll be like it's A. All right. That answer your question? Now, just a reminder that we did a problem like this, but we asked how much force would you have to apply in order to maintain a Faraday's loop spinning in a field. Well, we did it this way, but kind of worked at it from a different vantage point because we were talking about what you would have to do to maintain the speed of the rotation. So you can kind of see this. We're going to have a loop that has length L and width W. Is that okay? I want to maintain a constant velocity of V. All good? All right, so to do so, I want to start this problem by recognizing that the loop of wire already has velocity V. So that the moment it reaches the edge of our magnetic field strength B, and it begins to plunge into the region with the magnetic field, we know we're going to have an EMF. Ooh, that's terrible. An EMF that's equal to BWV. Now, this is from memorization. That's not proving it. If you want to prove it, then you have to use Faraday's law and the definition of flux to prove that it comes out to BWV. So we've done this several times already. However, would you guys like me to prove why you get BWV? Okay. So if that's the case, that's fine. The next step then is to figure out current, because the force that's going to be acted on that lead edge wire is going to be based on the current passing through that wire, not the EMF, which means the current that we're going to have in that wire will be the EMF divided by the resistance, which will be BWV divided by the resistance. Again, I'm having to make up things about this loop of wire because we need certain pieces of information. So, the loop now has resistance R over the entire loop. So, here's the thing. This lead wire right here is going to have a current passing through it. You should be able to determine the direction of that current based on Lenz's law. Remember, the direction of this current is to try and prevent the change in flux. There is no flux, and we're going to gain a flux that is out of the board. So the direction of that current should be to produce a magnetic field that is into the board. And the only way to do so is if the current in this portion of the loop is downwards. You can do this by also talking about the force on a charged particle, but again, I think it's better for you guys to use Lenz's law. But that also means that the current is in that direction as you try to go into that magnetic field. And that also means that the force from that magnetic field is going to be IW times B. Now the direction of that force comes right from right-hand rule again. Current in that loop is downwards, magnetic field out of the board. The force on that portion of the wire is going to be to the left. So suddenly, the moment I try to get into this region of space where there is a magnetic field, there will be a force on the wire in this direction. If I want the wire to travel at a constant velocity, I will have to apply a force in this direction that is equal but opposite so that the net force is 0. I push with force Fa. The magnetic field produces force B. Everybody follow along with that? And Fa equals Fb. Any question about that? How much work do I do pushing that loop into the magnetic field? Well, the work I do pushing that loop into the magnetic field is going to be Fa times L. That's how much work I do pushing that loop into the magnetic field. Force times distance. Simple enough. Any question about that? All right, well, we can talk about the energy dissipated in the loop. We know the power dissipated in the loop is going to be I squared R. We have an expression for I, though, which is going to be BWV over R. Right, this is the expression for I. If I square that, multiply by R, then this is going to give me the expression for the power that is dissipated in the loop as this loop passes into the magnetic field. Any question about that? All right, well, let's just B squared W squared V squared over R is the power. Well, work is power times time. In a situation where the power is a constant, if I can figure out how long it takes this loop to get in there, I could calculate the work done. Well, velocity times time equals distance. It's traveling at velocity v, and it's going to go distance L. So the time it's going to take to get in there, L over v. We still doing all right? All righty. So work's going to be B squared, W squared, V squared R times L over V. Well, what's all that about? Well, let's just take a look. So, Philip asked, about the energy stuff. So I'm just doing the energy stuff. Am I trying to show anything? Maybe. I'm showing all the different things that tend to show up when we talk about the energy stuff. So I can simplify this, and I will, but it doesn't get as simple as I'd like. V squared, W squared, VL over R. So what's the whole point? Well, are these things the same? Do I get the same amount of electrical energy discharged through the loop as I did physical energy on the system? We can figure it out. We have an expression for force over here. It's IWB. So this could be written as IWB times L. But I also have an expression for I. Right? Oops, that was ugly. But it's, maybe I can't. There's I, BWV over R. So that's BWV over R times WBL, which looks to be B squared W squared VL over R. So I tried to approach it from a slightly different perspective this time. Just to kind of work from it from both sides at once, but the amount of work that you have to do to push the loop in is going to be equivalent to the amount of energy dissipated through the loop. It's a point-for-point correspondence. And it's not saying that it's efficient, because that's the wrong word to use here. It just means that for every bit of physical work you do on the loop, you get an equal amount of electrical work done on the loop. Now, this is a consequence of conservation of energy, in that we can't get something for nothing. I can't just throw the loop at the magnetic field and I'll generate electricity without at some point losing that energy from someplace else. So I have to physically push the loop into the magnetic field. If I don't, and there's no applied force, then the loop will not maintain that velocity. It'll slow down, right? Because it's losing some kinetic energy. The loop has kinetic energy too. We could continue this idea that we had to give the loop some kinetic energy to start. The work done would take some of that kinetic energy away. Once the loop is actually inside the magnetic field, however, does it take a force to maintain the velocity of the loop inside the magnetic field? No, it does not. Because the moment the whole loop is in the magnetic field, there's no current in the loop.
Like electrical current?
That's the only kind of current there is in this class. Maybe in marine science there's other kinds of currents, but here not so much. Once the entire thing's in the magnetic field, there's no change in flux. If there's no change in flux, there's no generated EMF. There's no generated EMF, there's no current. So once it's in there, it can travel at a constant velocity, doesn't require a force to maintain its motion. Until we reach the edge. When we reach the edge of that loop and we try to get this loop out, suddenly that's all going to change. Us trying to get this loop out is going to do the reverse. Right? Suddenly, there's going to be a flux that's being reduced to zero. So I'm going to generate a current. That current will be in the opposite direction of the current I had before. As I try to pull this one out, I'm going to have a current that's going to now be in this direction on the leading edge and in this direction on the trailing edge. That's going to generate a force that's going to be in this direction on the trailing edge of that wire. If I want that wire to leave the magnetic field, I will have to apply an equal and opposite force in this direction to maintain the flow of that loop of wire outside the magnetic field. But if we have a non-uniform magnetic field, then the rate at which the flux is changing as the loop is plunging into that field is also not going to be constant. To maintain a constant velocity, we would probably have to apply a complex force to the system, because the force would probably be changing over time in this case still. You follow me? Although that might be related to where the loop is, I'm imagining a situation in which the magnetic field is getting stronger all the time. So we've got sparse, getting stronger all the time, right? We'd have to have some way of knowing how that magnetic field was getting stronger. But as I go in here, clearly the flux is changing, and the rate at which that flux would change would determine how much force we'd have to apply, because we'd be getting this constantly changing rate of flux inside the loop. So again, I'm not trying to demean the question. What I'm saying is, what are the merits? As a test writer, what do I gain by trying to ask this of you? I gain a complication for sure. I'm not sure it's necessary. I think if I'm trying to show conservation of energy, this might be the wrong way to go about it. And since the point of this question was conservation of energy, that's why I don't think that they would have that. Now, we did a problem like this. It had to do with the fact that the long current carrying wire was over here, and we asked questions about what did that mean to try and move this loop or to generate a current inside the loop due to that current carrying wire that was near it. That was a different question. And we weren't trying to worry about, how much force would you have to apply to maintain a constant velocity away from the loop. That, I think, would be a pretty complicated question. These are all pretty complicated questions. What are we fooling? Yes, sir.
In terms of for energy slash power, what is the prevalence of that on the exam? Like, is that like?
It's relatively low in this portion of the exam. I mean, they tend to focus that question more in the realm of circuit design, especially with resistors. But clearly it's been on the exam. You've seen some examples of it where it's been on the exam. But in a 15-point question, I think we're still pretty relegated to maybe only a couple of points possibly be related here. So I wouldn't get all hung up on it. But I would, if I were you, I would constantly remind yourself that power is related to work and time. Yes, there's derivative relationships here, blah, blah, blah. I know it's happening, right? It's the rate at which something is being consumed, in this case, energy. So if you're asked how much work is done, you should immediately be thinking that, all right, if it's an electrical circuit and they're asking me how much work is done, I'm probably being asked something about power. And understand then that you're going to need to know the time at which that takes, or something that binds like an absolute, like pulling it completely out of a magnetic field. There will be a finite amount of work done in doing so, because you're going to go from a state of there being current to there being no current. So I'd argue that there's ways to approach these problems, but just keep this idea in mind that power is a rate, work is an amount. Does that help? All right. Let's say the current in this wire is I naught e to the negative AT. All right. This is a situation in which the current in the wire is changing. That's going to produce a change in flux in that loop. What's the direction of the current produced in that loop based on the situation I've just described? It's going to be clockwise or counterclockwise. Do it in your head. Don't talk to the person next to you. Can you figure it out? And by the way, I didn't draw the direction of the current, but I implied it. So you've got to... Now, this is an excellent question in which they could say, what is the total amount of power dissipated in your loop from time equals 0 to time equals infinity? That's a way that we could calculate energy without ever doing this expression. You'd have to integrate it. That'd be a tough one, but the expression would have to be the derivative expression for power. That'd be a challenging question, I think. But I think some of you would still have a difficult time just calculating the flux here. We'd have to come up with this and that and this. We need some variables here in order to calculate the flux. Recognition that the magnetic field at a moment in time is mu naught I over 2 pi r.